Welcome back, mathematicians. We are looking at polar coordinates, and we have talked in the previous two videos about going back and forth between polar coordinates and rectangular coordinates and what that means. And we've also we've talked about graphing polar coordinates. We've talked about other ways of representing polar coordinates. Now we are at equations, taking equations that are written in polar form and rewriting them in rectangular form, or vice versa. So basically, I'm just going to take you through a bunch of examples. Now, here are the formulas we have talked about in terms of basically just the truths that we know from looking at what it means to describe a point in rectangular form versus polar form. And we took this picture, and with this picture, we came up, and things we already knew, like SOHCAHTOA, we came up with these four formulas. And generally, we use these two if we're trying to go from polar to rectangular form, and these two if we're going from rectangular form to polar form. But basically, at this point, we're just going to take an equation and we're going to see what works. So our first example is the equation 5x plus y equals 9. Okay, so I don't see a theta. I don't see an r. So this is definitely in rectangular form to begin with. And I'm going to use the fact that I know x is equal to r cosine theta and y is equal to r sine theta. So I'll just plug those in. Okay, now here's where it gets a little bit tricky. A lot of times with these, the question sort of becomes, how do you want me to leave it? Because this is a polar equation now. I've got it in polar form. But is that how I'm supposed to leave my final answer? And usually the answer is no. Generally, with polar form, you want to, if you have an r, because there are going to be times when you just have a theta, but if you have an r, usually we want to get r alone on one side, kind of like we like to solve for y when we have equations of lines sometimes. So basically, I'm going to take this and I'm going to solve for r. And the first thing that means is I'm going to factor an r out of both of those expressions on the left. And then I'm going to divide both sides by those two expressions. Didn't leave myself much room on the right. But basically now r is by itself, and this is how I want my final answer. It's not terribly intuitive. It's not something that you would say, oh yeah, naturally I want it like that. It almost really kind of looks a little prettier like this. So you kind of have to know that that's what you are going for, is that if you have an r and you have a theta, a lot of times you want to go ahead and get that r by itself. Because having the r by itself, it tells you, the r is telling you the radius of the circle. It's telling you a lot about the location. And that's what we have here. So this isn't actually a circle, but the radius tells you a lot, is what I guess I'm trying to say in so many words. So let's do another one like that. And it's not exactly like that. These can all be very different. You can have lots of different types of equations here that are starting out in rectangular form and you're being asked to put them in polar form. Again, I'm in rectangular here because remember, rectangular is x and y, and polar is r and theta. And this is rectangular form. Remember, x equals a number is just a vertical line. So that's what we're looking at here, is a vertical line. Well, if I know that x is the same as r cosine theta, then I'm just going to replace that with r cosine theta. And then again, if I don't know anything else I want to do with it, I might as well get the r alone. That tends to be our standard ending point. And there is my answer. Okay. Next up, this one should hopefully look a little bit more familiar to us from the start. Okay. Now, what I mean by that is, yes, it has an x and a y in it. Yes, it's rectangular, so I could plug in this and solve. But the reality is I actually already know something about x squared plus y squared. So since I have this over here, I'm going to take that and use that to my advantage and say, well, I know that x squared plus y squared is equal to r squared. And then I'm going to have to take the square root of both sides. And in this case, we don't have a negative because we don't have a negative radius of a circle. So this is my answer. Let me just do another one right here. Next one is a little bit more complicated. Looks a little similar to start, but it's definitely not going to simplify quite as easily. Okay, and in this one, I can't just look there and say, oh, that's the same thing, because it's not. So I am going to have to go ahead and plug in something for x and plug in something for y. And I will go ahead and do that. So that's r cosine theta squared plus r sine theta plus 5 all squared equals 25. This is going to get yuckier before it gets pretty. So it's getting messy at this point. So here we have r times cosine theta, and I'm squaring it. That's r squared times cosine squared of theta. Plus, this has to be multiplied out like two binomials being multiplied, which is what it is. It's r sine theta plus 5 times r sine theta plus 5. In other words, you're squaring a binomial, kind of like FOIL. So it's going to give me r squared sine squared theta, that's this one squared, plus 10 times r sine theta, plus 5 times 5, all equals 25. Okay, and if you don't believe me on that part, go ahead and take it off to the side somewhere. Sorry. R sine theta plus 5 times r sine theta plus 5, and go ahead and do your FOIL or distributive property, however you like to multiply two binomials. And that is where I got these things. Okay, so now I've got, let's see, r squared. I'm going to put these two together. I'm going to take an r squared out of both of them and then say cosine squared theta plus sine squared theta. Why am I doing that? Well, because for one thing, they both have an r squared in them. And for another thing, I happen to know that cosine squared plus sine squared is always equal to 1. That's one of my Pythagorean identities. Okay, and then I have plus 10 times r times sine theta. And then I've got plus 25 equals 25. So let's go ahead and get rid of 25 on both sides and get equals 0. So this, we just said, is going to be 1. So I have r squared plus 10r sine theta equals 0. Okay, so I just covered up below there where I had worked out this guy up here. And I noticed that there's an r in both terms. So now I have r plus 10 sine theta equals 0. I basically factored it. I factored out an r. Now when we factor to solve and we have it equal to 0, that's called the zero product property, and we set each of our factors equal to 0. This is a factor. So r equals 0, well, that's not even going to be a possibility because then I wouldn't have anything. And I definitely had something here. All right, so r plus 10 sine theta equals 0. That means r equals negative 10 times the sine of theta, and there is my answer. That one was a not pleasant one, and sometimes you get those. Okay, next up, let's do one that looks like this. X squared, oops, excuse me, started to write plus. I'm going to throw that out. X squared equals 6y. Okay, so I'm going to go ahead and plug in r cosine theta squared equals 6 times r sine theta. Okay, so this is r squared times cosine squared theta equals 6r sine theta. And this is another one I'm going to have to basically factor to solve. So let's see, let's move everything over on the left. So it equals 0. And then factor out an r. And I can go ahead and say, all right, I've got it factored, so either this is equal to 0 or this is equal to 0. If this is equal to 0, that's just the point at 0, 0, basically, right in the middle of the, it's called the pole, right in the middle of your polar coordinate grid. So we don't have that. We know we don't have that because this is not going to be, if you think about what this is, it looks kind of like a, well, not kind of like it, it's kind of like a sideways parabola. So r equals 0 is not an issue. So let's look at r cosine squared theta minus 6 sine theta equals 0. I can move the 6 sine theta back over. I can divide both sides by cosine squared theta. Remember, the goal here is to get r alone. And I have it. It is alone. So that's my answer. Messy, but true. Okay, let's get to one that's a little bit nicer. Let's do this. Okay, so I want you to think about what the polar coordinate grid or the polar coordinate graph, however you want to call it, looks like. And think about where theta equals 3 pi over 4 is. I'm probably copyright violating embeddedmath.com, but if you go there, maybe they'll be happy to get business off of me. So 3 pi over 4 is over here. It's not. I just went to the wrong line. Okay, let's say I didn't go to the wrong line. And let me find another one. 3 pi over 4 is right there. But it keeps going. It's a line. It goes through 0, 0, right in the middle, and it keeps going forever. Okay? So that's what a line, that's what theta equals an angle looks like. It's just a line that goes through the origin. So lines that go through the origin in rectangular form are going to be y equals some number times x. Okay, just y equals something times x. So just keeping that in mind, we can go ahead and, oh, I got some bleed through of my highlighter. Please excuse it. We can go ahead and solve it using the formulas as well. So here we have the only good one. Well, it's not the only. The one we're going to use is the one that has tangent theta equals y over x. So here's how we do that with this. This is kind of a little bit interesting. We take that theta equals whatever theta equals, and then we put a tan in front on both sides. Now, tangent of 3 pi over 4, I can figure that out. It's a unit circle value. The tangent of 3 pi over 4 is -1. Tangent of theta, well, that's y over x. So I can write y over x on this side. And then just like I said a second ago, with r, we like to get r alone. Well, when we're solving linear equations and we like have an x and a y, we tend to like to get y alone. So that's what we're going to do here. Go ahead and get, excuse me. And really, if the x was on top, we would get x alone. We just want to get this out of the denominator. It's always going to be y on top then. So multiply both sides by x, and we get y equals -1x. And that is a rectangular equation. Okay, notice it goes right through the origin. It has no y-intercept. That means because the y-intercept is 0. So that's that line, which is the line we just drew a second ago. So they really are the same thing. All right, let's look at another one. I'm running out of fresh paper. Got lots of paper I've written on here. How about r sine of theta equals 8? This one's a pretty easy one because it does look exactly like one of our formulas. So we can just say, well, that's y equals 8 and be done. What kind of line is that? It's a horizontal line. Okay, let's try another one that looks similar but isn't quite the same. Okay, r equals 9 cosecant of theta. All right, so cosecant is, remember, one of the two, cosecant and secant, we tend to think of as reciprocals of sine and cosine. Okay, cosecant is the one that goes with sine. So what I'm going to do is I'm going to put it into the denominator so that I can use that. In other words, I'm going to divide both sides by cosecant theta and say r over cosecant theta equals 9. Well, let's move that over here. I'm running out of vertical space. And this is the same as saying r times 1 over cosecant theta equals 9. Well, what's 1 over cosecant theta? That's sine of theta. So this is r times sine of theta equals 9. Well, we just found out up here, or we didn't find out, but we just used it already up here, the fact that r sine of theta has its own value, and that is y. And that is my answer here. It's another horizontal line. So basically, we've done a lot of different types of examples. We could keep going forever because there are a lot of different ways. There are infinitely many ways you could write one of these equations, but I think we've hit all of the basics, and you've seen how we can use these formulas to go from one to the other. One more thing I did want to show you is if you have an equation that's just, and we had one, let me see if I can find it. Okay, here's the one I was looking for, and I was going to say if you have an equation where it just ends up being r as a number, that's something you might be asked to graph. Ignore this side over here. And I just wanted to point out that, let's go ahead and put this over there, helps it make it ignorable. There we go. R equals 2. Well, the set that describes, any equation describes a set of points. That's the set of all points where the radius is 2. Which means it's the second circle out. So the equation of that, if you were asked to graph it, you would just draw a circle on the second circle out. If you were asked to graph r equals 3.5, you'd go halfway between third and fourth circles and draw a circle there. So if you have x squared plus y squared equals 4, you may remember from earlier this year that x squared plus y squared equals a number is the equation of a circle. That's how we write the equation of a circle that is centered at 0, 0. So it all comes together. This all makes sense together. And I hope it makes more sense for you right now than it did 17 minutes and 30 seconds ago. Thank you so much for coming, and come back another time and be good. Bye-bye.